Welcome back. I don't know if you could tell how excited I was about implicit differentiation for its ability to help us work with what otherwise would seem like impossibly bizarre situations. Part of that excitement was because of its ability to help us with this new topic, related rates. This related rates is really going to help us take calculus and use it to describe the world, and then use those descriptions to tell us new things about it through analysis. So what I'm talking about now is a word that's not a vocab word, but is worth bringing up: a model. So a model for us is not a beauty contestant. A model is a mathematical description of something in the world, like our model for the height of a falling object. So we've seen that before. We've done variations on this. And George Box has an amazing quote. He's a famous statistician, I think. All models are wrong, but some are useful. So, for instance, a falling object, the equations we've seen in the past don't incorporate wind resistance. And oftentimes, it doesn't matter. It doesn't matter if you're on a different planet, right? It's up to us as scientists to decide how appropriate is the level of detail for any given model, any given mathematical formula or formulation. So what we're going to see in this section is scenarios, usually in the world, sometimes just in geometry, and we are going to actually make the models for them. We're going to describe them with equations, and we're going to analyze those to get a result out, and then hopefully even, in many cases, say what that means about the real world. So this is a challenging thing. It involves multiple steps. It involves calculus, it involves algebra, it involves interpreting, often involves geometry. And each one of these presents its own problems, but this is challenging for all of the right reasons. It's really testing and growing your ability to make math interface with something in reality that for a moment can only exist in your head, and then comes out of your head and onto the page in a way that gives all the power of math to your pursuit. So, fair warning, this is historically a tricky but incredibly worthwhile topic. All right, here we go. Enough talking. Let's do an example. We'll talk a bit more about the places people get hung up in a minute. So, air is pumped into a spherical balloon. Again, most balloons aren't exactly spherical, but for this model, it's a good approximation. So that the volume increases at 100 centimeters cubed per second. How fast is the radius changing when the diameter is 50 centimeters? Okay, that's the situation. In any of these, you should really just take a minute and say, does this make sense? Can I kind of make a picture in my head of what is happening here? I'm blowing up a balloon. How fast? Well, I'm pumping in air in such a way that the volume increases. So I'm pumping in a constant volume of air. And then I want to know something different. How fast is the radius changing? And there's this weird relationship between the volume and the radius that we'll get to in a second. So step one is always just trying to read it and understand it. And usually in pursuit of that, the first thing I'm going to do is draw a picture. Let's make it a green balloon. So here's how I draw a sphere. If you've never learned how to draw a sphere, that's basically the trick to drawing a sphere. You draw a circle and then you do that kind of dotted line thing to show it's a sphere. So I've got a sphere, and this sphere is getting bigger. It's okay to draw it once and then come back to the drawing, but I can kind of tell already that I'm going to need a radius in here. So call this thing R. That's my radius. All right. Sometimes you won't realize all the variables you need until you start writing some other stuff. Let's go ahead. This is a related rates problem. And in any of these, they're going to give you a rate, and there's going to be a rate that you want. We're going to relate to rates. And I like to teach this where that's one of the first things you write down. So we're given a rate. What is it? Do you know? Looks like it's that the volume is increasing at 100 centimeters cubed per second. That's how fast the volume's changing, how quick this thing is blowing up. So let's go ahead and write this. We're given that rate. How do I write that rate? dv dt. Okay, and this should equal 100. All right, the rate I want is, well, it looks like I want to know how fast the radius is changing, so I want dr dt. Okay, as you start writing these things and as you're filling in this picture, I find it good to communicate what are the variables involved. So for instance, we already have that there's a V, that is my volume. There is an R, that's my radius. Do this for yourself, but also for whoever is reading this thing, because it's not always obvious what your choices are. You can label these whatever you want. V and R make sense in this case. There's a T already, which is time. There's also a diameter. I'm going to avoid labeling this diameter. I'm going to try not to use it too much, and we'll see why. But if you happen to write down diameter and label it, that is also okay. All right. Okay. I think that's about it for this one. But if I look at these rates, notice I said dV dt and dr dt. That tells me at the bare minimum I need a V, and I need an R, and I need a T, just to take care of that dV, that dr, and this dt. There is also this other given, which confuses people to no end. So this 50 centimeters, where does that go? And so I usually would put that in this want area because it's telling us something about what we want. You don't have to follow this kind of formula I'm giving you here, but the first couple of times, yeah, I think it's helpful. So we want this at, or when is, maybe when is the better time. When, I don't really want to have a diameter and a radius at the same time. So when R equals, do you know? If the diameter is 50, what is the radius? The diameter is twice the radius, so this should be a 25. Great. So I managed to get rid of that diameter, which might have caused me some confusion later. Okay. That's basically the information they gave me. And I've got this beautiful picture. Please draw a picture if it's not given for yourself and for the reader. It also helps in seeing what the variables are. Okay. What I want now is some relationship that ties this to this. If I know how fast my volume is changing, I should know how fast my radius is changing and vice versa. But that's not really obvious to me. That sounds pretty hard. So my relationship, in this case, is actually going to be something that connects not those derivatives, but V and R. I need some kind of a relationship between the volume of this sphere and the radius of this sphere. Okay, I'm going to give you a second. If you don't remember, look it up. Take a second. What is the radius of a sphere? I'm going to start now. There's a V equals, there's definitely a pi. It's a volume, and radius is a length, so you're going to have an R cubed for the volume. And frankly, if you get that R cubed right, you are most of the way there. Your problem will basically be right. The question is, do you remember what number goes in front? All right. I won't normally take this much time, but it is this fun number, 4/3. Okay. So for some people, it is just remembering their old geometry that is going to be a big struggle for them in this section. And so each time you encounter one of these, try to get it lodged in your head best that you can. I often just remember this as, for some reason, is that its derivative is 4 pi r squared. But we're going to have cones, we're going to have cylinders, we're going to have boxes, just basic shapes. And the more of those you can get in your head, the easier this will be. Okay, so we've got this relationship. Why do we have this relationship? Because that's enough to know the relationship between these rates. How do I go from one to the other? I need to implicitly differentiate it. So here I go. I'm going to implicitly differentiate with respect to time. So I'm going to say, looks like dv dt is equal to 4/3 pi. That's just a constant, so that just hangs out. The derivative of r with respect to t is 3r squared. Now r is just a function of time, so I do my chain rule on it. I need the derivative of this inner thing called the radius, and that is dr dt. Take a second, inhale that. That's our implicit differentiation in action. And what we just got out was a relationship between the derivative of v and the derivative of r, those two different rates of change. If we know their static relationship, we can get a relationship from their rates of change by implicitly differentiating. That is so smart. That is so clever. This is how models in math often work, right? We start with something that we can write easily, and then via some calculus or differential equations, we get to the thing that we want. All right, this is pretty great. It's tempting right now to maybe solve for a bunch of stuff. In the end, what we really want is this dr dt. And it's tempting to solve for it. I'm going to recommend right now that before you even bother to solve, we plug in like crazy. So once you take the derivative, then you can plug in. So we have some information. It looks like we have this dv dt is 100, and we want it when r is 25. So let's plug in and say this is 100 equals 4/3 pi times 3 times 25 squared times dr dt. All right. Once you take the derivative, then you can plug in, because now we're saying what's the value of the derivative at that point in time when r is 25. If you plug in these numbers before, if you plug in those two numbers before, all of a sudden what you have is a constant on the left and a constant on the right. And if you take the derivative, you just get 0 because you fixed them in time. And the moment you fix them in time, nothing is changing. Okay. So implicitly differentiate, then plug in, not the other way around. It's one of the bigger mistakes because it really breaks your whole problem. We're almost there. We plugged in. Now we just want to solve. What for? The thing we want, dr dt. So let's be really lazy about this. It looks like dr dt is equal to 100 over everything on the right is 4/3 pi times 3 times 25 squared. Yeah, that's it. That is my rate of change. We can definitely clean this up. We can get a decimal approximation. That's not bad. Let's clean up a little bit here. Why? Because it looks like those two 3's are going to cancel. And 4 times 25 is 100. So here to show you what I mean. This 3 cancels with this 3. One of those 25's times a 4 is 100. And so that's going to cancel with this. And so we should get a 1 over 25 pi. Ta-da! All right. That number right now probably doesn't mean a whole lot to you, but this relationship is amazing that we got it all. You could solve for dr dt way up here if you wanted to learn something deeper about how the volume changes with respect to how the radius changes and vice versa. That's how you get some deep insight into the relationship between volume and radius. In terms of just finding an answer fast, yeah, plug in and then solve, right? So solve and plug in is it's just more time consuming, but it does tell you something a little bit more deep. Okay, that is it for this first big example. Let's just recap the steps. We read a beautiful, if often at first confusing situation. We took a deep breath. We tried to draw a model for it. Once we thought we were starting to get a handle of it, sometimes just draw and add a variable, go slow. We identified what rate we wanted. The rate we're given. We identified the rate we wanted. And usually the one we want is going to happen at some particular moment. So when r is 25. Okay, this is the thing we're going to plug in after. As you're doing this, make sure to check back in with your drawing and that all important things are labeled. This will also tell you what variables really need to be in there. So volume, radius, and time. Please do let whoever's reading it know what those are, because you get to make them up. It's your model. Okay, then we need some kind of relationship that's going to relate these two. So something that we can take the derivative of. So in this case, that volume is related to radius via my volume formula for a sphere. Once I get that, I take the derivative to get a relationship between my rates. Once I take that derivative, I'm allowed to plug in these fun numbers, and then I just solve for the rate I want. Very, very cool. I don't know, it's just such a different, neat thing that ends up being so powerful. In the end, what this is telling you is that the rate of change of my radius is 1 over 25 pi, which is a fairly small number. If you want to go back and track the units, then the units here are going to be centimeters per second. So it is worth at the beginning making sure that we are in similar units the whole way through. All right, that is it for this first video. The rest of this lesson is really just going to be examples, just videos of examples. Hopefully each time you take more of an ownership of the process, you try to do it more yourself, and you could just get happier every time you do it. Okay, that's it for now. As you're working through this and it's confusing, also be honest with yourself about which part is confusing, because usually it's not the whole thing. Often it's just the geometry, like trying to remember what relationship you need to use. Okay, more on the next video.